Today we're going to study the inductor. In every day of our life, we see a lot of inductors. I drive the Tesla to work every morning, and I have a very powerful 215 kilowatt motor at the back of the car that converts the chemical energy of the batteries into kinetic energy of the car. So what is really inductance? Inductance occurs when current flows through a conductor. Here we have a current I of t that goes through a wire. As we all know, it will generate a magnetic field according to the right-hand rule. The magnetic field would circle around the conductor according to this right-hand rule. Now the current flowing through the conductor set up a magnetic field that is proportional to the current. The voltage difference across the conductor is proportional to the rate of change of the magnetic field. So what we have here is basically a very simple equation that the magnetic field phi or magnetic flux is equal to the inductance times the current, I sub t. And what you have in this statement here, the voltage difference, V of t, which is the voltage across these 2 points of the wire, is equal to the rate of change of the magnetic flux, and therefore is equal to L di of dt. So you have this very basic differential equation, which is V of t is equal to L di dt. Now, let me just restate that. The voltage difference across the inductor is proportional to the rate of change of the current, di dt. The proportionality constant is called inductance, denoted by L, and the unit of L is named after Professor Henry of Princeton. H is equal to volt second divided by ampere. And this is apparent from this equation here, because L would have the unit of volt second divided by ampere. This is a repeat of what we have shown. Very often inductors are represented by magnetic coils, very much similar to this coil we have here. So this coil here, the positive terminal, the negative terminal, and this has about 100 turns of copper wires. You have a voltage across the positive terminal and the negative terminal. And this voltage is induced by the change, the rate of change of current that is flowing through the inductor, according to the equation V of t is equal to L di dt. Similar to the capacitor, we have a differential relationship between I and V. We also have an integral relationship between I and V. If you look at the differential equation, what you have is that V of t integrated over time, V of x dx integrated from time t0 to t, would be equal to the current. At the beginning, the current has an initial condition of I of t0 at time t0, and the amount of current increase would be equal to 1 over L times the integration of Vx dx from time t0 to time t. So this is another way. If you know the V of x, then you can find I of t by this integral formula. If you know I of t, then you can find V of x using the differential form of the relationship between V and I. We also have a very similar equation that we have looked at before. For capacitor, W of C is equal to 1/2 of CV squared of T. For inductors, we have 1/2 of Li squared. So let us just compare these for capacitors. We have W of C is equal of T is equal to 1/2 of CV squared of T. Whereas for inductor, we have W of L of T is equal to 1/2 of Li squared of T. Now, we derived this equation last time. We can likewise derive the equation here by noting that the integration from time 0 to t of P of x dx is the power integrated over time and therefore is equal to W of L of T. And likewise, we have, on this case here, if you look at from 0 to t, power is equal to I of x times V of x dx. So if you make the substitution that V of x is equal to L di of x dx, and then you have then the dx here. Again, by integration by part, very similar to last time, we will have 1/2 of Li squared of t. And therefore, this equation is now proved. Let me give you a few examples here. For example, if we have a current through a 1 Henry inductor, it's given by I of t equal to 0.45 ampere, cosine 2 pi 60 t. 60 is basically the 60 hertz of the AC current. We are required to find V of t, the power P of t, and also the energy that is stored in the inductor over time. Now, in order to find V of t, we know that V of t is equal to L di t dt. So what you have here is that given I of t is that, all you need to do is a differentiation with respect to time, and then multiply that by L, and then you would have V of t equal to L di dt equal to minus 1 Henry. The minus comes from differentiation of the cosine, give you a minus sign, 0.45 ampere times differentiation of the argument of the cosine function, give you 2 pi 60 sine 2 pi 60 t. So after simplification, you got V of t equal to minus 169.7 volt times sine 2 pi 60 t. So what you have is the initial current is given by the red curve, whereas the voltage is almost 170 is given by the blue curve. So this is the voltage, this is the current. And what you find is that this is a cosine function with a zero phase at time t equals 0. This is a sine minus sine function with a value of 0 at time t equals 0. The voltage, we call the voltage lagging after the current by a phase of 90 degrees. How about the power? Well, power is equal to I times V. So we have the V given by this that we have derived, and the I is given by this in the example. So what you have the power P, and what you can do is that you can do a sum of angle formula on the sine x cosine x, and therefore it becomes sine 2x. You have, instead of 2 pi 60 t, you become 4 pi 60 t. And then you combine all the rest, you got P of t equal to minus 38.2 watt as a sine function at twice the frequency of the initial voltage. So again, you can look at this. The example here is that the power actually oscillates at double the frequency of the voltage. Finally, we can look at also the amount of energy that is stored inside the capacitor given by 1/2 of Li squared. And after simplification, what you have is that this again has a double frequency. This is a square of a cosine, which can be expressed in terms of a double angle formula into the sum of 1 plus the cosine double frequency term here. So if you look finally at the energy store, what you have here is that because you have a 1 here, and the cosine function ranges from positive 1 to negative 1. So at certain time, this cancels out exactly this, giving you therefore an exactly a zero energy store. Energy cannot go negative, and it can have a peak, and so it is a raised cosine function. And that's the amount of energy that you have stored inside the inductor. Let me give you another example. What is wrong with this plot if I of t is the current through an inductor? So what you have here is that you have the current that is initially at 1 ampere going for a constant of 1 second, and then switch to minus 1 ampere for the duration from 1 second to 2 seconds. Now, as we all know by now, that the voltage induced across the inductor is proportional to the rate of change of the current. Now, given the fact that this is flat, there's no change of the current, and therefore the voltage would then be equal to 0. So you have a 0 voltage across the inductor from times 0 to 1 second. Likewise, there's no change of current through the inductor from 1 second to 2 seconds, therefore there's no voltage across the inductor either. The question here is, what is wrong with this plot? It's wrong at these points, basically at time t equals 0, at time t equal to 1 second, and also at time equal to 2 seconds. What you have here is the rate of change of the current with respect to time is infinite. dV, dt, di, dt, the rate of change of current at this point is infinity, and therefore C equal to L di dt, V is equal to L di dt, the I di dt is infinite, and therefore you have an infinite voltage. And that's not quite possible. What it says here is basically that you cannot instantaneously change the current flow by an abrupt step in an inductor, because that would induce an infinite voltage. So we can do a reflective exercise. We can summarize the voltage-current relationship and the formula for energy stored for capacitor inductor. We've done that, which is basically the capacitor is 1/2 Cv squared, whereas an inductor is 1/2 of Li squared. These are called dual relationship because they have the same equation, except that you have in the inductor is Li squared, whereas for the capacitor is Cv squared. Describe a situation in which a current with either a capacitor or an inductor has time-varying voltage across its elements, even though all sources are constant. I'll leave that to you as an exercise that you need to think about it yourself. Next, we're going to do an experiment to illustrate in real life how inductance occurs.